Hi everybody, I'm Dmitry Chuyko, a guy from St. Petersburg Oracle Development Center, performance team. Maybe someone know that I presented some talk about Java util concurrent in Java 8 last year. So now it's a missed part about CompletableFuture. One more new thing that's actually not new, as it's in public release for a long time. But anyway, let's talk about it. The agenda is quite fluent, while I hope we will have time to discuss important things. This slide says that I may say anything and I won't get hurt. So you won't make any business decisions based on what I say. All right. You all came to know something about CompletableFuture, but who still writes single-threaded applications? Well done. Are they JDK 8 or like JDK 5, 6? No matter. Yep, just a few guys. While I know several long-living single-threaded applications, but everyone has to write code that is multi-threaded and it's parallel, and Java instantly had tools for that. So let's briefly remember what we had in Java 1. It was just a few concepts, basic representation for threads, and related primitives. So we had synchronized blocks, wait notify, and so on. In Java 5, we had additional primitives for synchronization and keeping shared state correct. So if we use things like semaphores or some concurrent queues, they help us to keep our shared state correct when we do concurrent programming. Also, in Java util concurrent, there is an executors framework that allow to convert some business logic represented by inner classes originally, runnable and callable descendants, to some tasks that are executed asynchronously. And yeah, now they can use lambdas, as Java 8 has lambdas. And what we got Future. What was mentioned that it's not the endpoint because in Java 7 for join pool was introduced, and it's a way to arrange work stealing between tasks. Then tasks that threads that have spare resources help busy threads to get their job done. And if you think about that, you will understand that the direction of evolution here is to first add some valuable things, new capabilities, and to hide complexity and to hide explicit parallelism. I will mention this some next slides, but whoever actually needs some main thread. So think about that. your application doesn't need any main thread. You just need to synchronize correctly your output and your input. Anything else can be done more or less in parallel. So we got Future. Basically, Future is all about result it holds, and it helps to control blocking of the thread that get results, and it provides a result itself and some way to know about errors. So just look at the code. I think you're all familiar with it. So in any program that utilizes executors, you'll see something like that. Just create some task, some callable in this case, and somewhere else get its result. Well, don't forget to check your exceptions. Let's assume we are parsing some file and getting its content asynchronously, reloaded it with some other thread, and now we should process everything that happened there. And what we get? We get some execution exception that contains, in a good case, of course, some information about exceptions that occurred inside that our magic callable. So I think you'll recall personally some guys who write things like this. I recall myself. So just a typical approach, then we can combine futures recursively and to wrap results of nested futures. And in many cases, it's required to process some general errors that we can met during execution. Well, now we have lambdas, we have almost functional programming. Let's be mature, let's use callbacks. Create some function that processes one function for success, one function for error handling, and pass them into some asynchronous routine. In this case, we are also reading file. So is it good? No. Because let's assume we have to process the contents they get also asynchronously. And maybe we should also do something asynchronously after that. So we get structure of one or even more layers. And if you can see, we have repeating code here. We do same thing. We must write it twice, because in such approach there are no language facilities to do it better. Okay, but who needs ever to work with that structure? Let's work with flat structure, no nested levels. That's possible. That's how we use CompletableFuture. So here is the same task of loading file contents and processing it, both asynchronously, at least in the thread other than our current thread. And here we combine those two processing tasks. using utility methods, and handle possible problems in one place. I think it's nice. So, what actually do we see? We see some method chaining. Look, there's no intermediate values, no defined locals. Less code, that's good. We all know that technique, because everyone saw, I think, tens or maybe thousands of builders in some enterprise projects, maybe some generated ones, or at least just string builders, some Moxon unit tests, and of course Java 8 streams. So they all apply this technique. And we worked with multiple futures, as I said. You can count that each element in the chain means future, completable future. All right, so let's do a bit more formal approach. Let's talk about API. CompletableFuture has a rather big set of methods, while it's a standalone class. And many may say that, yeah, why there are no this kind of methods or this kind of methods, but it is actually considered having enough functionality to cover necessary cases. So the class itself, it's a part of core library in Java CE8. It implements future, so we can use it as a future of type of necessary type. There is a new interface called completion stage. It describes some general approach to building completable future. If you look into source code, you'll see that all JavaDoc, most of JavaDoc, and is located in the completion stage, and most public methods are there. Not all of them, but most of public methods of completable future are present in this interface. It describes a stage of some computation consisting of many stages that you can combine and get valuable result dividing our work. There is also some interesting method to completable future that is some common basis that allow to use implementation facilities that allow to work with completable future and apply them to any completion stage. So in many methods we can use some completion stage instead of completable future. All right, we are talking about completable future, but how do we get it? We saw one method of getting completable future. It's submission using a supply async function, but there are simpler cases. Future can be created directly, so it's an interface, and implementations are obtained from some factories like executors. But completable future may be just constructed with constructor, and it can be passed anywhere. some arbitrary thread may complete it, or many threads may complete it. Only one will get success, but that's not a problem. We can create something that someone will complete, and we had nice options to deal with it. Even more, we can create already completed future. Who knows why? Okay, it's just a way to get standard building brick without any hard work. It's just a trick to do less code scaffolding about if-else and so on. And the way that I showed previously is synchronous submission of some tasks. Just like for our well-known future, they can be described as, for example, runnable. And we can see here methods like supply async and run async. They have formed with explicit executor and without it. In implicit case, it's fork join common pool, and that's good because we use common well-sized warmed-up pool. And on next slides, if you see a function that ends with async, that typically means that result, that execution may not be done in the same thread that previous actions were done. But if you create future, it's implied by default. Alright, let's call that methods. It's that simple. We can just create a completable future that will represent a task of calculating, very hard of course, 42 long value in a common pool. And another one is just some utility completable future that contains already pre-calculated 42 value. Oh, this is concurrency, this is hard. This is complex. I already know. All right. What is good about streams? They have clean abstractions of transforming our values without any intermediate locals, and those concepts are quite few. So the same is for completable future. Maybe the most common method is then apply, and it's rather than apply async. Then we can pass some function defined, of course, typically by some lambda, and that will create new task and return completable future that will describe both those tasks, and the result will be a transformation of first result by the supplied function. So sounds maybe a bit complex, but if you look at the code, it's simple. So what's done here? We start some asynchronous calculation of 42, and then start some asynchronous calculation of result of calculation of 42 and plus in this magic number. Nothing complex. A good completable future will describe result of all calculations. So CompletableFuture in Java contains aspects of listenable future. So there are, in some sense, terminated terminal methods that do not return value. So you see void here. It's then accept and then run. Then you can finally process the result of your calculation chain. It's then accept. Or just ignore it and do something. Then your calculations have completed successfully. Is then run. So in this case, we accept printing to standard output. Isn't that simple? It's my most popular question today. Please, if you have questions, ask, because the hard part is not yet. All right. Yeah. So maybe I missed this point that transformation methods correspond to abstraction of mapping, like map in streams. We just convert something that describes one value to something that describes another value. So if we may have map, why don't we have reduce? We do. We can take results of to the completable futures and combine them using some function. All right. Let's calculate two hard values, 42 and 2015, and calculate minimum. In this case, then combine is in form without async, so minimum will be calculated inside thread pool, but in the same thread as hosting future. Yeah. I can see here three threads. Right. For first future, second one for supply async, and the third one is for combine. Am I wrong? No, you're wrong here, because it's not in async form. I think we can just check that. It's not the principal question. But generally, if you see a method without async suffix, it's executed in the same thread of its hosting future. So it's cheaper. We can even not start a new task. We can do work in the same task if we already get another arguments. Or we can keep our thread from blocking on parking and parking in thread pool, and that helps us to utilize our resources better. All right. Yeah.
About cheaper, but that means that first we just calculate the supply since 32, then we just run method then combine, and only then we start supply sync to some.
No. Because Java is not symbolic language. If we mention some argument, it should be calculated before we start, execute, and then combine.
That means that we wait. We started for second thread, first thread ending.
We wait for submission. Supply async is a function that does submission.
Submit, and then we just submit a second calculation.
Yeah.
And the
So we sub it.
To submission ending, then after the end,
It will be completed after their completion. So we submit 2 tasks, and we submit 3rd task that consumes their results.
so the main equation is that are this first supply sync and the second supply sync start both in parallel
Yeah,
from the beginning.
yeah, they are. Assume they are rather long-running complex operations. So supply is cheap, while the operation itself is expensive. Right.
And then combine it start after submission and then submit a second thread.
All right. That's a good question because that's the point.
People start understand, yes.
The methods that are not present in complete stage interface allow us to work with collections of completable futures. Sometimes you need to quickly understand, are you okay with all a set of some futures, or maybe some of them, who's faster. So if you look at signature, you will notice that, of course, the result of each method corresponds to common sense. So if we need all or any, we'll get something that's generally an object, or anything that can be expressed just as void, as we can deal with it. All right, the complex part. Be ready. Then compose. To better understand this method, you should recall a flat map in streams. Then you have stream of streams, and you do a flat map, and you chain that streams into one single string without any nested structure, consisting just of plain values. Here we do the same thing. First, you can look at the code that's slower. Then we create completable future that returns completable future. We saw a callback hell. This is a helly situation too. It's hard to deal with this. But there is a solution. We can call then compose, supply a function, and returned completable future will be interpreted in terms of its result. So framework does work for us. I think the example with numbers is quite clear. Please ask questions, because it's hard part. All right. Look at this. First, we supply calculation of some value. That's simple. The result is a plain value. And then they have a function that maps different values to some asynchronous tasks, because it may involve some next complex calculations, maybe in different thread pool. Because all async methods may operate with different pools.
So it's like then applied, but asynchronous tasks.
Not quite wet. It's method to hide complexity of nested tasks. So here we have one task that starts another itself. look at this. X is mapped to CompletableFuture supply sync. So supply sync is done inside execution of some other asynchronously supplied code. And generally, if we do then apply, in this case, we'll get CompletableFuture of CompletableFuture. But we have a way to flatten this into CompletableFuture of original primitive type. Oh, all right. More questions?
So the CompletableFuture composed in second supply sync will consume the result of first supply sync.
Yeah.
And the result is CompletableFuture of the second supply sync.
It will start some synchronous calculation. This result is provided by CompletableFuture that's returned by supply sync. Yeah.
The second one. Supply sync.
Yeah. So we understand what we should get here, right? We should get a sum. But how do we access that sum? In the case of second code, we should do get, right? And the first one, we just do get, and we don't care. Was there any additional CompletableFuture started inside some asynchronous code? No, we just have that one. All right, what about get? We know that future provides get, and CompletableFuture is a future. So right, it has get. And it works the same way. It's blocking, it throws all the exceptions. It's the same get we know. It also has a version with timeout, with all the same exceptions. It has an interesting option to try get value immediately without blocking, and return default in case it's not available yet. And we also have a nice method join. There is a problem using futures with streams, because get throws exceptions. Check it once. So fluent string containing some string transformations breaks the exception handling that we must do in case of checked exceptions in Java. So there is a join method that just doesn't throw the exceptions and basically does the same work as get. You see an example here. All right. We've already talked about some cost of submission, something asynchronously, what's that cheap operation, supply sync, and some expensive operation that calculates something. What's expensive? I just did some trivial benchmarking on my machine. Here's the configuration. I used JMH harness, so it's very well written and allows you to get correct results with your measurements of performance. So please use it. The benchmark description is pretty straightforward. There are two parameters that define the backoff for two simple operations. Operations just return values, but they burn CPU cycles. It's an utility method, black hole consume CPU. It's not sleep. It's actually not eliminated by compiler cycle that do some arithmetic operations. The simplest one is sequential calculation of multiplication, A times B. So this is a first benchmark. We can do some simple implicit parallelism with stream. Or we cannot do this. You can see parallel stream and just a stream that maps two integers to two values and reduces resultant stream to a multiplication. Are there any questions? You can see there are no threads. By the way, in the last year, whoever started new thread in some production code? No, just production code that contains new thread start. All right, a few people. I think that's good. Try not to do this. All right. Implementation with Future. Just our well-known Future. We use common pool from for join pool just to have ability to compare results in some sense. So streams will use this by default, and CompletableFuture will use this. So we submit, in first case, two asynchronous tasks, block on both of them, and calculate result in our main thread. Another option is to submit third task that will block and get result and get its result. So it's a combination. And CompletableFuture variant, again, we may independently submit two completable futures, work in a blocking fashion, just like with plain future. No difference, but nicer code. And another good option is to combine them using then combine and supply a third future that will calculate multiplication. All right, results. Look at this. It's microseconds per operation. We see, of course, a lower is better. We see that sequential operation of multiplication A and B, its first line, takes about 5 microseconds, while futures take 12 and 13. So it looks like futures are not that good, right? Right. In this case, we have a very big cost of trade-offs. Let's do a more lightweight operation to estimate what's actually the cost of empty completable future in this case. And we submit 2 or 3 futures into common thread pool. So you see it's up to 8 or 9 microseconds, comparing to almost nothing for sequential case. There it is 5 nanoseconds. So you see 1,000 times difference. All right, let's create more heavyweight calculations and try to benefit from parallelism. It works. You see the greater value of parameters that describe backoff. And we can see that, yeah, paralleling by 2 gives, of course, not 2x, but some valuable impact, right? AB is about 600 and CompletableFuture 3. It's then combine and then apply. It's 342. That's good, because lower is better, and this is score in microseconds per operations. All right. We have some time. Let's look at web. I just took something available as a reference implementation from java.net. It's Jersey, a reference implementation of JAX-RS, and it's run with Grizzly and Naya framework. The combination can be easily obtained by creating a Marin archetype and doing some minimal changes. And of course, our secret sauce, that's CompletableFuture. I'll better show you code using ID. Or not. All right. We have some main class. Oh, who uses Node.js and some other managed? All right, guys. You should like this. Just a simple way of start some server that accepts connections and reacts and responds something. We just start Grizzly and it automatically discovers our annotated resources and waits for input to terminate. We have an endpoint that responds. I will show it in browser. It's completely honest. We inject some data service, and it's a kind of interesting one because it doesn't return plain Java objects as we typically do. Is it typical? Oh, I think yes. Here is a method that describes behavior in case of GET request. It returns some text, and the text is a combination of two data pieces. So the data service consists of some pool. It's required. It will be required next. It has two methods that return CompletableFuture of string. First is find audience, and second is find impression. So there are some independent data pieces that easily may be some query to database. Just to make some complex work, wrap it as a CompletableFuture, and return as promise. Look at this. Here we create CompletableFuture just like I described in the very beginning, using its constructor. But then we do some magic. We schedule some task that's actually a CompletableFuture, and it tries to complete our future with the result of some hard operation. In this case, it's file I/O. And also it catches any problems and completes exceptionally our promise. So supplier of our promise gets clean view of what happens. He gets a result or the original exception. Look at this. In this service, we combine two CompletableFutures. We know nothing at this time. what is their state? Are they successful or not? Are they executing or not? They just operate the futures, not their results. We just know that then results will be available. We will combine them. So then combine. They know how we will do this. We will just concatenate the result strings. And then they will pass that result to user who sends HTTP request to our server. It's async response resume. And in case of error, we also respond to user, but he'll get a processed exception because the second response resume operates the throwable. Those two are different methods. So you see two method references, both described with async response resume. The first one deals with some correct result, an object, and second one deals with throwable. Types are inferred in this case. All right. And here is a small part that describes working with timeouts. If you have some long operation, you must provide any way of not waiting for its completion infinitely. So how it can be done with CompletableFuture? First way is to use is not actually use CompletableFuture, but use the possibility that's provided by the async response itself. So we set timeout handler and return some exception using same resume method with throwable parameter. Another way is to get additional parallel thread. So in this case, it's defined as an executor that may be injected, but it's not. And we schedule some task. It's scheduled with delay of 1 second. And it completes exceptionally the same promise that we created, as I described earlier. Different threads having same promise object. One of them either completes it with the result that's file contents, or with exception because timeout happened. And this works. That's nice. All right, let's look into the code. Just to show that I'm not cheating. That's all. This guy, and this guy. All right. So, let's start our server. Blah, 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 blah. It's already running. Oops. Just a moment. Let's check that results that you already see. I'll press refresh with the mouse. All right, request failed. What we were trying to do? We were trying to read two files. Look at data service. One is named audience and another is named impression. Look into this. I don't see audience file. I see audience txt. Let's rename it. And restart our server. We actually might not restart on it, just use the same console. I think that's all. That really works. All right. Any additional questions? Time's up. No. Take them. Ping me personal.